So we're good?
Let's just double check first. Okay, you can click the thing. I'm just gonna wait for it. Excellent. It's live? So, you can do the intro, and then, yeah, just hold
I think you have to speak into this.
Do the double one. Hello everyone, welcome to UQCS's, whatever week this is, week 10? Week 10 talk. We've got your favorite lecturer, UQ Computer Science lecturer Paul Vrbik today, and he's going to give a talk about recursion. Hope you guys enjoy this one.
I'll just take this. You guys can hear me enough if I speak like this? Don't have to speak with the mic. How many of you are from my 1001 class? Okay, you may have seen this talk already. Okay, so this is basically like a condensed version of the recursion talk I gave in 1001. We're going to do a couple sort of more harder examples, and I'll assume sort of higher level of Python competency than I can assume in that class. So let's just get her going. Okay, so what's recursion? Okay, when a function calls itself, it's a recursive function. It's as plain as simple as that, right? And this may seem strange because, like, how can you have a function utilize its own self in the definition of that function? But it's logically sound, and it's logically sound for reasons that we'll get to. But first, I sort of want to describe recursion through memes, which is sort of obligatory. So recursion, it recurs, recursion, it recurs, recursion, it recurs, right? So recursion is just some type of self-reference, right? So that's what this meme is trying to sort of get. Is this a recursion? Is this a recursion? Is this a recursion, right? I usually add myself into this, right, if I can. If you search recursion on Google, that's actually going to ask, did you mean recursion, right? So you can get trolled by Google. I'm not sure if you guys still study from old dead dinosaurs, these things called books, but I got trolled by a book in the same way. In my data structures book, I looked in the index for recursion, and it kept bringing me back to the index, right? I didn't understand what was happening until I realized that recursion was referring to itself in the index for recursion. So I got trolled by, the obligatory Drake meme, right? We want to have recursive memes and not recursive memes. I like how Phantom Menace is back in the cultural imagination, right? So we're going to write recursive functions with a base case. Look, with a base case, and having a base case is going to be important, right? This meme is actually showing you something called bottoming out, right? Which is sort of the analog of having an infinite loop, right? So the main parts of a recursion is that we're going to have a self-reference. That self-reference has to be something smaller, and eventually there's going to have to be something that's the smallest, right? So we're going to start here. To understand recursion, one must first understand recursion, which may seem facetious, but I think this is sort of one of the big stumbling blocks of I find students really avoid this as a technique, even though it's a beautiful and extremely powerful technique, especially when you pair it with caching, right, to get dynamic programming, or pairing it with backtracking, which we're going to do. So why does it work? Well, really, it's the analog of the principle of mathematical induction. And so most of you, if not all of you, should have taken Math 1081 or something like the discrete math course, right? So you've seen the principle of mathematical induction. You probably showed that the sum of the first n numbers is equal to n times n plus 1/2, something like that. That seems to ring a bell, right? I have this problem, and so I teach 3400, which is the class specifically about recursion in the third year. And the first problem I give them about induction is something that's geometric, right? Because I feel that somehow everyone believes that induction can only be utilized on arithmetic, right? And and people don't understand induction. Like, I've had big arguments with people who aren't pure mathematicians, who don't believe this works. Why do we need induction? Does anyone know, like, why this was provisioned as a proof technique in the first place? Like, when do we need this? Like, why can't we just direct prove everything? Yeah, so like you have some statement P, like in this case, and like the statement is sort of a truth statement, right? So you give me a natural number, and that P of that natural number is either true or false. So it's something like Pn is the statement, the sum of the first n numbers is n times n plus 1 over 2. And we require this if we need to prove a proposition is true an infinite number of times, a countably infinite number of times. So it's a very powerful technique in that sense. And the hang up is this, right? So how you prove something is true an infinite number of times is that you prove that it's true once, right? Basically at the floor for n equals 0. And then most people get hung up over this statement here. You have to prove that if it's true at the nth statement, then it's also true at the thing that comes after n. But this seems strange, right? Because you have to write something in your proof that sort of says, assume Pn. And it's like, I thought that was the thing that we're trying to prove. But it's not, you're not assuming n, you're assuming n as the sort of antecedent as this inference statement. So think about it this way. If you want to prove A implies B, what's the first statement in your proof? You guys should take 1061, I guess. Okay, if you want to prove A implies B, the first thing you do is assume A. Assume the truth of A and show consequent to that the truth of B. So in this induction, we're not assuming n is true, period. We're saying if it is true at the nth step, then it is true at the nth plus 1 step. If that statement is true, right? If it's true at 0, and you have a rule that says if it's true at n, then it's also true at n plus 1, then it is true for every single natural number on that predicate statement, right? So the reason I'm telling you this is because recursion and induction are like two sides of the same coin, right? In Comp 3400, we take inductions and we turn them into algorithms. If you can prove something is true using induction, you have a recursive algorithm basically handed to you. All right, so here is the proof that I asked my Comp 3400 students to do because it totally thwarts them. There's no equation. They're like, how am I supposed to prove this? There's no equation that I can assert the correctness of, right? So here's the setup. Take a chessboard, remove any piece that you want. I'm going to give you a tetramino or trinomino. It's this, you know how you have dominoes? That's actually a wider category of things called ominoes, right? You can have, there's one domino. I think there's two trinominos, and this is one of them, this hook piece. So here's the statement. If you remove one if you remove one square from a chessboard, it's possible to tile the remainder of the chessboard so that only one piece is removed. Do you believe me? I can do it for this. Okay, prove that you can do this on any board that's 2n by 2n. So how are you going to do this? By producing an infinite number of example boards? Of course not. Okay, so here's how you have to think about this. What's the base case? So this is the other weird part about why people don't want to use recursion. They never go deep enough. Yes?
Was it 2 to the power of 0?
Yeah, so what size board is that?
1 by 1.
How many tiles does it take to tile that if you remove one square? There's one square, it's gone. How many tiles do we need? None, right? Like, so, okay, so this is very important though. They're like, well, this isn't a tiling. How can the absence of tiles be a tiling? I'm like, does this satisfy the condition? Is every square covered aside from the one that we removed? Yes, and this is going to correspond to a base case in a recursion that's totally trivial, right? So the one thing I teach my 3400 group to do is to go deep, right? They always want to, normally my students in 3400 refuse to give this as the base case. They give the 2 by 2 board as the base case because they can actively place a tile. But you don't actually break anything by going to 0. This satisfies the condition of covering anything, right? So a vacuous tiling, an empty tiling satisfies that condition. Okay, what's the next part of the induction that feels weird, right? Remember, I want to prove that this is going to work for 2n by 2n boards. So what do we have to assume as a starting point? Or what do we have to show in our induction here? Yeah.
Assume that a board that is the size of 2 to the power of n times 2 to the power of n works.
Exactly. Okay, assume already that if we have a 2n by 2n board and remove a square that we can tile it. We just assume that. The analog to here, when you're programming this with a function, is to assume the function already works. That is a very powerful philosophy to be at play when you're designing recursive functions. A lot of people try to think about the whole recursive stack through. That's like reaching through the abstraction barrier. When you're programming a recursive function, it works already. It gives you back the thing that you want. This is equivalent to assuming the sort of antecedent in this induction. Okay, how can we prove it then? So I need to utilize the two facts now, or at least the one fact. Here's a 2n by 2n board. I've removed a square. Can you somehow give me an argument that I can tile this board now, utilizing the fact that we can cover 2n by 2n boards? What happens if I cut this into 4 pieces like this? What are the sides of the subboards?
2n by 2n.
2n by 2n. What's true about a 2n by 2n board? It can be tiled. So does that mean I can tile this one? There's one square removed. Okay, but what about the remaining boards? Can I tile them? Okay, but I can tile them in such a way that only one square is going to be left uncovered. So here's the whole trick, right? And usually the induction or the recursion comes down to figuring out how to connect the solution that's one less than you to the current level. And this is how you would do this connection. You would place the tile here. And what does placing a tile there in effect do to those three boards? Well, that's sort of like the square that we can presume has been removed. And if that square has been removed, what's true about those three subboards? They're a 2n by 2n board with one squared removed, and therefore they're tileable by our induction. Right, so this is the first problem that I normally give 3400. I have them prove this, which they find a little bit unpleasant because there's no equation that they can write down, but the induction still is at play nonetheless. But then furthermore, on assignment 2, I say you have the now program it. Now give me a program that will actually tile this board. And I would do it, it just gets sort of in the weeds. But I challenge you to go home and try to program something like this, right? The base case would be very easy, right? If n is equal to 0, return the empty tiling, right? A board with a 0 in it or something like that. Otherwise, assume that you can get tilings for boards that are smaller, and then you just have to sort of connect them somehow. Okay, so here we're going to just do a bunch of recursions, right? So every recursion must have at least one of the following, right? You have to have at least a base case, right? There has to be some smallest problem that you're solving, and you should make sure that smallest problem is totally trivial, right? Because you're programming it, right? So you want to go all the way to the bottom. It's going to sort of feel uncomfortable sometimes because these vacuous cases are always kind of feel weird. It feels weird to say that, yes, there is a tiling of the board which requires 0 tilings. And then you want to have a recursive step. Like, as I said, what's necessary in recursion is to have a function call itself. And the function that calls itself has to call itself with smaller input. That is necessary, right? Because what happens, and then if that function calls itself, it's going to call itself with smaller input. So each time you're calling on smaller input, you have a base case, which is going to be somehow the smallest input. So that's how everything ends up working, right? So the canonical example here is the factorial function. Like, I'm sure you've all seen this. Who knows what this sort of represents from combinatorics? Yes?
It's just like 3 times 2 times 1. It's just n times n minus 1 times n minus 1.
Yeah, exactly. So it's like 3 factorials, 3 times 2 times 1 times 1. But like, what is it physically representing?
Ordering n elements?
Yeah, if you give me n unique elements, n factorial is the number of ways that you can order them, right? Because there's n options for the first placement, n minus 1 options for the second, right? And I ask this because if you have 0 items, how many ways can you order them? One way. It's the absence of order. Like, here is the ordering, right? So that's why 0 factorial is 1. Like, in this case, there is a sort of physical analog that we can understand. But another valid way of saying why is 0 factorial of 1 is because if it was anything else, we wouldn't have the pattern satisfied, right? So don't forget that a lot of times when we're defining things, we get to make that definition, right? So if you had 2 to the power of k, right? That's naturally recursive. 2 to the power of k is 2 times 2 to the power of k minus 1. But that eventually has to hit a smallest case. What's the smallest power that you can put something to? 2 to the power of 0. What's 2 to the power of 0? 1. Why? Because if it's anything else, that it wouldn't satisfy the pattern. That's really the reasoning behind it, right? So don't forget that, like, we're empowered when we define these recursive functions. We get to pick what the base case is going to be, and we should pick it so that the base case is easy to program and that it satisfies the inevitable pattern, right? So if you wanted to implement this in Python, you do it like this, right? I'm saying, okay, give me n. Here's our base case, right? If n is the smallest thing that it can possibly be, 0, then return 1. Otherwise, return n times factorial of n minus 1. And here you see we're recursing, and the argument is smaller than the argument that's coming in, right? So these have the 2 ingredients of recursion, and therefore it's going to stop. Now, in order to trace this is you just assume this works. Right? So if you were tracing this, I would say, does this work? I would say, is it the case? Let's just assume factorial of n minus 1 returns n minus 1 factorial. If I multiply that by n, do you get n factorial? Yes. That's the level of analysis you need to work at when working with recursion. Okay, so if you called a factorial of 0, you're going to get 1. If you call factorial of 3, you're going to get 6. If you call factorial of minus 1, what happens? Yeah, well, okay, you recurse out, right? So like maybe you need preconditions here, but this is called bottoming out, right? That we don't call it an infinite loop in recursion. It's trying to find a bottom which doesn't exist, right? So this is why this is called bottoming out. Normally, this is why your computer is going to have some type of recursion limit, right? Because this is worse than a infinite loop. Why? Yes, right. An infinite loop does not require more memory every time you iterate. Every time this function calls itself, what does it do? You should know by this point that you have a function stack, right? So you keep allocating more and more memory every time you call this, right? So a recursive function that calls itself infinite amount of times, if it wasn't gated somehow, it could potentially like occupy all of the memory, or at least all of the memory allocated by for that process, right? So it's more dangerous to have a function that recurses all infinitely than it is to have a while loop that recurses infinitely. Okay, I'm just going to show you how this actually works, but I don't want you to think like this when ultimately programming recursively, right? But you should see how it happens once, right? So this is what Python would do. It would say, what's the factorial of 4? Well, that's 4 times factorial of 3. Factorial of 3 is 3 times factorial of 2. Factorial of 2 is 2 times factorial of 1. Factorial of 1 is 1 times factorial of 0. And factorial of 0 is the bottom, right? So that gets replaced, right? So this is called the winding phase of recursion. And it's one of the deficiencies of recursion, actually, that you have to allocate all of this memory, right, to make all of these function calls. But then ultimately what happens is after you wind, you start unwinding, right? So now Python can say, okay, so factorial of 0 really turns into 1. And then we know that the order of arithmetic here happens by brackets, right? So the most interior brackets get expanded, and then you get 2 times 1, 3 times 2, 4 times 6, 24. Right, so these are how these recursions work. You make all of these calls, you build this recursive stack, you make the final call, which is to its base case, and then it unwinds, right? So this is called the winding and unwinding phase. Okay, so what I want to do now is actually like program some recursive functions, right? So we can learn how to do this in practice. And I want to make sure we go all the way to the bottom. Remember, the base case we have to program it. So I want to program something that is absolutely trivial. So the way that you sort of can do this, if you feel uncomfortable, is you go to the first case where you feel comfortable and backwards engineer what the base case should be, right? So for example, this is the definition for powering, right? 2 to the power of k is the same thing as 2 times the power of 2k minus 1, right? So it's basically multiplying 2 against itself k many times. Now, I can ask the question, what should it mean to multiply 2 against itself 0 many times? And we could all scratch our heads about this, but really, we know 2 to the power of 1 has to be 2. We know 2 to the power of 2 has to be 4, right? So if we know and feel comfortable with 2 to the power of 1 being equal to 2, and we know 2 to the power of 1 is 2 times 2 to the power of 0, then we deduce from this that 2 to the power of 0 has to be 1, right? You should pick a vacuous base case which makes your pattern work. But many students I have will make this the base case because they feel this is the one that's obvious, right? This one sort of feels weird and yucky. But it's like, no, that's what it has to be in order to fulfill the pattern. And furthermore, we have no restriction that k has to be greater than 0, right? So often I'll have to deduct marks for people because I've said, unless you're willing to put a precondition into your powering that says you're not allowed to power anything, you have to take powers of stuff that are non-zero. It's not really fulfilling the spec, right? Okay, so what should the base cases be in practice? Well, what are the smallest versions of your data types? For integers, it's usually 0. For list, it's usually empty list. For string, it's usually empty string, right? In Python, this is sort of easy to denote because, you know, truthy falsy? Anything in Python is true or false. It doesn't matter what it is, right? And anything that's falsy usually is the smallest thing in your data type on purpose. Because if you go back here, look at my factorial function. You see how I made that test, if not n? If not n is going to detect 0 or the smallest thing in most objects. Usually that's the thing that's going to be falsy, right? So it's very idiomatic now to test for your base case. Your base case is always going to be the thing that is false in your object if you set it up properly, right? So usually the base case is going to be something like if not n, right? If n was a list, it would still be working. If n was a string, that would still be detecting empty string. So it was set up very, very deliberately. Okay. Okay, so here, let's solve some problems using recursion. I'm just going to give you like the way that we're going to think about this. When we're going to do this, we're going to assume the function already works the way that we want it to work, except that it works on smaller input. Do not try and understand how the whole function is going to work. That's like trying to understand the induction all the way to the base case. The first step of induction is just to assume P of n already works. The proposition at n is already true. My function is already working for smaller input. How? Who cares? Magic, right? Or induction really is the answer to that question. The second piece of advice is we want our base case to be the smallest possible thing, right? And it's going to feel weird, but if you don't feel weird, you probably haven't gone small enough, right? And if you can't figure out what it should be, we're just going to go to the first case where we feel comfortable working with, and then backwards engineer what that base case has to be. Okay, so the first one is this. How can we flatten a list? All right, so I'm just going to do some programming now. Okay, so everyone can see that. I hope that's large enough. Okay, so what did I say are the two components of recursion? We need a base case, that's the smallest thing, and we need to sort of like self-reference, right? So what is the smallest flattening problem that we can solve? Do you not agree that if I said you get to pick any list for flattening, which one would you pick if you had to be correct about how you flatten that list, right? The empty list, right? So how can I detect empty list? What's the Python statement for this? Yeah, if not X's. That's it. This will detect if the list is empty. That's why it's been set up like this. Exactly so we could say this. Okay, so what is the output if we flatten an empty list? Return, not 0. Return the empty list, right? That's how we flatten the empty list. Okay, so now we have to think about it this way. We have this list, and suppose we can flatten something smaller than that. And the thing that's going to be smaller is smaller by length. So if we already know how to flatten lists so that are smaller than the one that's smaller than our input, how can that help us flatten the list here? Okay, so I'm going to do this. So here, this basically catches empty list. Empty list. So this means that at line 13, I know that the list isn't empty. That's kind of important, right? Because if you want to index into something, you need a precondition saying that you're able to index into it. So I'm going to break it up into its head and tail. Its head is x is at 0, right? That's safe, right? No index error because that would have been caught at 10. And the tail is what? A list slice. I love this stuff. And this is going to work even if the list doesn't have 2 elements, because that will return empty if there's only 1 element in it, right? So both of those operations are safe. Okay, so suppose we can flatten the tail. That just works. Just pretend, like we just assume that it works, because by definition, the tail is going to be 1 less than the length of the input. So just this works, right? By magic. How can we utilize that to get the flattening of the whole list? Yeah.
I think appended to the end of the head.
Yes, okay, but what happens if the head's also a list? Right, so here I said that this was 1, but we can imagine this was sort of 1 minus 1 here.
I think what we return from that is flattened head, and then appended to that is flattened tail.
Exactly. Okay, so let's do this. We can say if the type of head is not a list, right? Or is not a list, then head is a scalar, right? So here we can say return head. Whoops, I gotta move this up. Plus flatten the tail. Okay, otherwise what? So at this point, we know that head is a list, right? So can I just say flatten head plus flatten tail? Is this going to work? Let's see. All right, flatten this. Okay, as if by magic, it just works. right? Because I just assumed, like, this is working. How? Who cares, right? Induction is the answer to that question, right? But lots of people get stuck here trying to in their programming of this, try and work out how the recursive stacks are going to resolve. And I'm saying, don't care. Just assume it works. And if you have that philosophy when programming, then you'll be able to program recursive functions. Okay, let's do another one. Whoops. Sum the digits of a number. 1, 2, 3 is 1 plus 2 plus 3 is equal to 6. Can we do this recursively? Any ideas? Okay, so n is an integer. What's the smallest integer? Okay, I guess maybe we have to make sure that, well, minus float infinity. Okay, we'll just say we're assuming that there are no negatives, right? N is greater than or equal to 0. Okay, so what's the greatest non-negative integer? Exactly. Like these answers should be obvious, right? Okay, so how can I do a test if my number is 0? If not n, that's the 0 check, right? The base case is always looking exactly the same. If the number coming in is 0, what's the sum of its digits? Okay, so that's super easy to program, right? The base case should require no programming. The base case should be absolutely obvious. Okay, so we have the smallest problem now, right? We know that the sum of digits of 0 is 0. Okay, now the problem is we now have to take 1, 2, 3 and sort of create a smaller problem that we can recurse on. Okay, but think about it like this. What happens if I could break 1, 2, 3 into 1, 2, and 3? Could that help us at all? Okay, so if I could break that into 1, 2, and 3, the answer would be what? 3 plus the sum of digits of 12, right? Okay, how do I get 3 out of 1, 2, 3? Modulo 10. All right. Modulo 10, that's 3. How do I get 12 out of 1, 2, 3? Integer divide by 10. All right, so sum of digits and divided by 10. Is this going to work? Let's take a look. Sum of digits. 1, 3, 6, 7, 11. Okay? And this doesn't even really need to, like, you could pack this into one line if you want. But again, all I did is I specified what the solution was to the absolute easiest problem. And then I just used the function as if it was working without caring how the thing gets resolved, because it's just induction, right? You get to assume the function already works for smaller input. Okay, so that was a good warm-up. Now I want to solve this problem. And I'm promising you it's going to be as easy as the two things that we just did if we lean into this philosophy. So are you familiar with this Towers of Hanoi problem? Okay, so I'm just going to specify it. Well, how are you familiar with it? Oh, okay. But for those of you who didn't take 3400, how are you familiar with this? 1061, yeah. So like this is like one of the prototypical examples of induction, right? Because you get to do something that's visual that you don't necessarily get a nice equation, which sort of undergraduates can get pigeonholed into thinking that induction is for. Would you be able to write a function for solving the Towers of Hanoi if I asked you to? If you had to bet money on it, right? You think you'd be able to do it if I gave you... Okay, so we're going to do it. And I promise you, if we just lean into our philosophy, it's going to be quite easy. All right, so here's the statement. So what we need to do is move this stack of disks from peg 0 to peg 2. And we only get to move one disk at a time, and the only constraint is that no bigger disk can go over a smaller disk, right? So, okay, something that I'm hiding behind here is you also have to be quite clever about what your function is returning, right, in order for you to be able to utilize it recursively. So in this case, doing this move encoding is going to be the thing that enables me to write a very streamlined function. And so I don't want to sort of hide that complexity away, right? So if you want to write a recursive function, you have to think hard about what you want returned to you that is going to help you construct a solution at that level. And in this case, I think, I want a move set to be returned to me as lists. Because I think in the end of that, I want to concatenate those lists. right, in order to sort of describe the move set, right? So I'm going to describe the move set like this. So we're going to have pegs 0, 1, and 2, and I'm going to number the disks 1, 2, 3, 4, right, based on their size. So that's disk 1, disk 2, disk 3, disk 4, okay? So this move encodes move disk 1 to peg 1. This move says move disk 2 to peg 2. This move says move disk 1 to peg 2, and so on and so forth, right? So does everyone sort of see the encoding? And everyone agreed that I just solved the Towers of Hanoi problem for 4. Okay, so what I want to do now is write a recursive function that solves the Towers of Hanoi problem for n disks, right? We're going to sort of say, and I'm going to do it like this. I'm going to say, I want to solve the Towers of Hanoi problem for 4 disks labeled 1, 2, 3, and 4. And I'm being a little bit more clever here. I'm going to solve a more generic problem by saying I'm going to solve the problem of moving from peg 0 to peg 2. Right? Not just always assuming I'm moving from peg 0 to peg 2. Okay, so the first question is, what is the smallest Towers of Hanoi problem?
Moving a single disk.
Not deep enough, right?
Empty towers.
No disks, right? Here is your solution. It takes no moves to move no disks from any peg to any other peg. That's the absence of moves. But that's informative, right? Because people always want to go to the first thing where you're actively doing something, but you would have to code something. What do I have to code? Nothing. Okay, but that's important when you're programming, right? This base case is going to be not screw upable, right? So how do I check this base case? If not n, return the empty list. That's what I want, yeah.
Side question, why is using not and Pythonic and not like if n is equal to 0? Why is...
Because this basically detects the smallest or vacuous object in any single, right?
So it's basically equivalent to using, finding like the most, finding out if the given value is the most falsy.
Is the only falsy usually, and the only falsy is usually the empty thing in the set.
It's just that for clarity's sake, why would we not use if n equals 0?
Because then you have to have a number class, and if I use not n, then it works for anything. So don't forget that Python isn't a typed language, right? So one is actually much more flexible than the other. I agree for you, like, so I usually do this, right, in my code because it's not unclear, because it's more clear to do this, right? I'm not the biggest fan of like doing zero checks like this, but it is Pythonic, it is PEP 8, and the answer is it's more generic, right? You're not necessarily assuming that the type that you're checking is of a certain type, but it leans into this, like, this is why falsy truthy was sort of provisioned, right, in a way. But I'm not going to pretend that it's more clear, but it is Pythonic, right? So you can bring it up with the PEP 8 people about why this is the case. But the fact that Python isn't a typed language always sort of like throws a spanner in the works. Like this becomes relevant in COM 3400 too, when there's type inference engines, where if you did something like this, then you're enforcing the fact that n here has to be something for which a zero check exists. Okay, because you can imagine I could have a Hanoi that like would be happy enough to return a tuple in addition to returning a list, right? And I don't want to have to like maintain two different ones. But in any case, so here's our basic case, right? If we want to move zero disks from any peg to any other peg, it's the absence of a move set. Okay, so here we go. Okay, if we can move 4 disks, can we move 5?
If we can prove, if we can prove that we can do it for n disks, we can do it for n plus 1.
Yeah, so I can't really draw n disks. So like n in this case is 5, n minus 1 is 4, right? So I'm really trying to think about what this means for the induction. So here are 5 disks, right? Can we move, if we basically take for granted that I can move 4 of them, can I solve this question for 5? How?
Move the top 4 to the middle peg, the bottom 1 to the final peg, and then stack on top of the...
Okay, so that's how we're going to code it. Okay? Okay, but there's some things that we have to discuss here, right? So there's peg, so we're trying to solve this problem in general. I'm not necessarily going from peg 0 to peg 2. I'm going from one of the pegs to one of the other pegs, right? So there's, I'm going to call this the peg that, so we want to move from this peg to this peg, and I'm going to call this the other peg. Okay, so if the pegs are numbered 0, 1, and 2, all right, so we have to do this. Okay, so we have from peg, target peg. What's the other peg? Okay, so let's think about this. If I want to move from peg 0 to peg, if I want to move from peg 0 to the target peg 2, what's the other peg? Yeah, but like what number is it? So I want to go from peg 0 to peg 2. What's the peg that's not those two things? 1. Okay. If I want to move from peg 1 to peg 2, what's the peg that I get to use? Okay, so it's 3 minus from peg minus the target peg. That is always going to be the one that's left over. You can convince yourself by going through all of the permutations. I believe that's correct, right? So if I want to go from 0 to 2, 1's the leftover one. From 1 to 2, 0's the leftover one. Did I leave anyone else out? It's all going to work out. Okay, so we have the other peg, the from peg, and the target peg. Okay, so I want to move n disks now. So how did we say that we were going to do this? If I want to move n things, well, I want to move, all right. I want to move n minus 1 of those disks, right, from this peg to the other peg, yeah? And then I want to move the largest disk to the target peg. What move is that? Well, that's the largest disk, and that's the move to the target peg. Is it not in my encoding? It's always the disk that we want to move into to its target. Okay. Whoopsie. All right. I was gonna put some brackets around here just so I can go like this. All right. So we move n minus 1 disks from the peg to the auxiliary peg or to the other peg. Then I move the largest disk to the target peg. And now what do I do? Well, now I need to move the n minus 1 disks. Where are they sitting? On the other peg. And where are they going? To the target peg. And I think that should be good. Okay. Whoops. I have an extra bracket.
You're missing a plus of 1.
Oh, thank you. Okay, so can I move forward? Okay, let's see. Can I move 1 disk from peg 0 to peg 2? Cool. Can I move 2 disks from peg 0 to peg 2? Okay, so move the smallest one to the middle, move the biggest one to the end, now move the thing in the middle to the end. Okay, can we do 4? Okay, let's just remember 1, 1, 2, 2, 1, 2, 3, 1. Was that sort of what we can confirm? 1, 1, 2, 2, 1, 2, 3, 1. Right? Can we solve this for more? There you go. How many lines of code? 2? Right? Does line 41 even count as a line of code? That's just basically some arithmetic, right? So, but this is just really leading it, like this was something that I think maybe people wouldn't have been able, like without recursion, this could have been hopeless. Like I think the only non-recursive solutions is to basically simulate recursion using a while loop and popping and pushing and like that. But all we did here is, again, all the other things that I said that we were doing. Just assume that it works, delineate what the smallest problem is, and then write your code. Just write your code assuming that the function is already working. That's like about the most powerful strategy when working with recursion that I can give you. Now you're gonna have to give some thought about like what that function should be returning. Again, the fact that it was returning a moveset like this was sort of deliberate. Like I wanted to be able to interject by concatenating these two lists, but there it goes. Okay. What else do we got? Solve Sudoku. Okay, so like what is the philosophy going to be here? We have to give some more thought to what we mean by smallest. Okay, so I wrote a bunch of code before, and we're going to have access to a bunch of things. Like here's some boards. Okay, like I can pretty print them. Okay. I think I can check if there's a winning condition. Okay, I can, get a grid. I can say, in this board, what are the grid numbers if I go to the position 2, 3, and it'll return back those grid positions. Okay, so maybe we don't think about what's smallest here. Maybe we think about what is the easiest Sudoku board that you can, if I wanted to give you a Sudoku board to solve, what Sudoku board would you want to be given to solve it? No. Other side, yeah. Already solved Sudoku board will require the minimum amount of solutions by our code, right? So basically I want something that says, if has one board, right? Then we're done. Return true. Right? Easy peasy, right? I don't want to do anything, right? The base case should always be vacuous. Okay, so we're going to do something called backtracking here, which means that the way that I've set this up is sort of important. I said, look, this solver is going to produce. I'm going to give you a board, and you're going to in place solve that board, and return true when that's possible. And if it isn't possible, I want you to return false and revert the board back to its original state. Okay, so so now we can assume we're given a board. It has some blank entries in it. I want to solve something that's smaller. What does smaller mean in this case? Less empty spaces, I guess. Right, so I want to put something into the board and then try to solve it. Okay, so what should I try to put in the board? Okay, so what we need to do is I need to find an empty position in the board. Okay, so and we'll say empty position is none. For I row in enumerate the board. Okay, so the board is a list of lists. Each list is a row. Okay, so for J, I don't care in enumerate. What is this? Row. Okay. We need to find an empty position, right? So if the board at ij is none, right, then I can say the empty position is at ij. And we don't have to break out. We can just let it go through the whole board. It's not very big. This is going to find maybe the last empty position. Okay, so now I have an empty position in the board. What should I try to put in the board? Okay, now the simplest version here, I want to do something like 4k in range 1 through 9. Go to the board at ij, put in k, and then try to solve that board. Okay? My computer's not fast. This will work technically, but it's too slow, right? So we have to do a little bit better than just going through all the numbers. So everyone familiar with how this sort of works? How Sudoku works? Okay, so basically what I want to do here is just figure out what are the candidates, right? So I want to look at what row I'm in, and it can't be any of the numbers in that row. I want to look at the column I'm in, and it can't be any of the numbers in that column. Okay, so what row is this? Okay, the row is the board at I. What column are we? So that should be the board at this column. Oh, sorry, J. For all of the rows, right? So for I in range 9, I guess. We can, but it turns out this is already enough to be fast enough, right? Yeah, but I can do a grid if you want. So I actually have, that's why I have that, I think, yeah, grid. I can ask for what's the grid at this board at ij. That's exactly what that's going to do. Right, so I think 0, it's row column. So second row, third column is here. Yeah, so it was giving that. Okay, so anyways, that will be the grid. So then the candidates should be what? Candidates are, all right, k plus, so it's k for k in range. So what numbers are we allowed to choose? 1 through 9, so don't forget, right, exclusive. If not k in row plus row plus column plus grid. Okay, I just have to do something here. So if we go through this whole board and don't find an empty position, it's full. But if it's full and we haven't triggered this condition, then we basically say if not empty position. If there are no empty positions in the grid and we haven't formally caught it, then this is false. Right? Just return false. Okay. So I'm going to go through all of the candidates here. I'm going to put a candidate in, and I'm going to try to solve the board. And I'm going to say if the board is solved, then return true. Otherwise, if we get to here, we failed at solving the board, right? So I say, okay, sorry, we revert this back to what it originally was. There should have been a none here, and return false. Okay, so let's see. Let's see. I hope I didn't screw this up. It'd be very satisfying if this worked. Okay, so here's okay, let's go step by step. So here's B naught. It's already solved. So that shouldn't. Okay, true. Here's B1. Okay, can we solve B1? Oh, what? Oh, there's a bug. Where's my bug? I don't want to have to hit my emergency button yet. Put board for K and candidates. Put that in. Solve the board. If solve the board, return true. That's right. Okay, well, maybe I didn't save. Let's see. Solve. Here's B1. Solve B1. Ah! Did anyone see my mistake? There must be a simple mistake. Let's just look at the solutions here. What did I do?
Does grid return a multi-dimensional array?
No.
I think I saw it. Can you go back?
Yeah.
Yeah, it's if not empty pause return has one board.
Yeah, but that shouldn't. If not, because okay, I'll try to put that in, but that shouldn't have really made a difference. It just reduced the number of lines. Okay, but I'll try putting that in. I just wanted to emphasize that there is a base condition, but okay, let's see. I really want this to work. Solve B1. No. K for K in range 1 through 10. If not, K in row plus column because grid. There has to be a small mistake here. Anyone see the... Or maybe I'm pulling the column out wrong. It's always something like that. Ah, yeah, yes. Okay, so all I did was I was extracting columns wrong. Do you see my mistake? I did IJ. I should have reversed that. Okay, so I think that actually fixed it. Okay, so didn't quite get my punchline. But okay, so let's solve B1. Come on.
Well, it's time to give up on recursion and use
Yeah, give up on recursion. Let me just do this.
Setting the RJ to empty pause.
Where?
Above row, right above row.
Yeah.
I will just be the last I.
Oh, geez, yeah, something basic. IJ is equal to empty pause. Yes, I didn't unpack IJ. Oh, yes, it was always going to be the last. Okay. No, we still not give up yet, team. Okay. Ha. Yeah. Pretty print. Print board. B1. Okay, so here's B2. That's how it looks like. Pretty print solve. Oh wait, no, that won't work. Okay, solve B2. Okay, wait, I'll do this. So these are actually ordered in rank of supposedly how hard they are to solve. So there's B2. Let's solve B2. Now let's print that. Okay, I'll do one more. So pretty print board. There's B3. Solve B3. Oh, took a little bit longer. Print board B3. Okay, but this isn't a very complicated piece of code, right? You would think this would be a lot more difficult for solving Sudoku, and I think probably one of the hardest pieces of the code that was abstracted was getting rid of this grid. But I can show you, we don't really it was sufficient computationally speaking. to exclude that. Yeah. Right, so like the most satisfying thing would have been for me to put range 1 through 10 here. That would have been like so dumb. If my computer was faster, that would have worked. But I want, okay, maybe we can even take out columns. Like maybe it's enough to even just not do the most stupid thing. I haven't tried this. Let's see. Yeah, now it's thinking a little bit harder. Okay, so probably rows and columns seem to be at least necessary, but grid wasn't necessary, right? Like you could be asked this at a coding interview, and you could spin something like this up quite easily. But the whole thing sort of comes down to like calling solve on like using solve in order to solve the Sudoku board. Right, and having a little bit of an imagination of what smallest meant in this context. Smallest by measurement of how many empty squares there were left. Yeah.
Just from what do we put in empty board and
Try to solve an empty board.
Or a single number board, because I know that a few of those are possible.
Well, aren't those easier to solve because there's less constraints? Like the empty board is the easiest Sudoku board to solve because you're totally unconstrained. But I don't actually know. Okay, so let's see. Is there a clever way to do this? I have to deep copy. Oh geez, I just okay. Hold on. I just have to type this out. I'll just put it here.
Just also, so this solving this recursion, so that the lowest thing at the end there, was it board ij equals none, that's kind of like a backtracking thing?
That's the backtracking. Like the fact that I said, hey, listen, if you can't do it, revert the board back to what it was. So this is like a larger category. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll talk like the last thing I want to finish with is dynamic programming, and I do want to get there because decorators are really cool.
Probably have the column thing back.
Okay, so that's a board, right? That's that board. Can we solve B none? I don't know. This may be an edge case I didn't account for. What colon?
You see the column, see the column.
Line numbers, please. Oh, right. Yes. Oh, yeah. Thank you, class. All right. Ah! That's probably the canonical one. See, but this is the other amazing thing about programming recursively. It usually covers the base cases that you're not thinking about, right? In fact, I trained someone to do an interview at Amazon, and we did it, and I trained her to do it dynamically. And like one of the problems that they gave her was just to induce all these crazy edge cases, and she did it recursively utilizing float inf, which is a very powerful constant to use, and it totally thwarted them. They like didn't believe that it worked, and every single traced work, right? So this is a very effective interview strategy, code interview strategy, because you're writing so few lines of code. Yeah.
You think if you were to run it again using like you re-empty the board again and you run it again, you return a different result or the same result?
No, there's no randomness in here, so I can return a different result.
Okay.
Yeah. Yeah.
If you were to change the order, in like for example, you know that.
Yes, if I were to commute lines of this code, then maybe the outcome would be different. Yeah. I can't say for sure if it would be different or not, but.
I was thinking like, if you were to change where it would find where that empty position would be, like, maybe it's the.
Oh yeah, if I like ask for the first empty position but like there's no way to double break is the problem. I was kind of lazy. Like I'm trying to write like the simplest pieces of code that will work, and like who cares in a board of 81. Okay, there's just one more thing I want to show before I go. Okay, we'll just delete all of this. Okay, so Fibonacci sequence, right? Is everyone familiar with this? Okay, so every number is the sum of the previous two numbers, correct? So this is like prototypically, this is a recursive example with highly overlapping subsequences. So what's this? So the base case here is like if n is less than 2, return n. Right, if n is 0, return 0. If n is 1, return 1. Otherwise, it's return fib of n minus 1 plus fib of n minus 2. I just have to go down here and grab. Okay. So I'm going to run it. I'm going to run fib of 30 10 times. I'll do fib of 25 maybe. Okay. Okay, that's actually still pretty fast. 28. Whoops. Oh, okay, maybe I can go a little bit higher. Okay, let's try 30. I hope this is not crazy. I see. Okay, about a second to do that 10 times. Now this is where recursion starts falling apart, right? You're like spinning up all of these stacks. This is going to have, and like furthermore, like in order to compute Fibonacci of like 28, you're going to be recomputing like the same Fibonacci number over and over again. Okay, so the strategy here then is to use a cache, right? And use a cache, and I say, and basically you can put your base cases in here. I can say, the Fibonacci at 0 is 1, Fibonacci at 1 is 1. And then we rewrite this to sort of, instead of computing everything, you say, look, first check if it's in the cache, right? If n is in the cache, right? And actually, it's better if we do this. If not n is in the cache, then go ahead and compute it. And then put it in the cache, right? For n. And then just return what's in the cache. Right, so this means we're saving old solutions. Okay, so whereas that took 1 second about, if I do this, it's now taking way less than that. Okay, but that's not the punchline here. Do you guys know what Python decorators are? Okay, so this is something else that you can do. Okay, so you go to your programming interview, you write this function, they say, how do you make this fast? And you have like 30 seconds left to make this a dynamic program. I literally did this at my Google interview. Okay, so there's these things called decorators. I can't talk about them too much, but basically in Python, functions are objects, right? And anything that's an object can be an argument to a function. Okay, so this thing that we just did where I put a cache over a function is a pattern. And any recursive function getting a cache is going to get it in the same way. You're going to put a cache in its global space. You're going to have it read into the cache beforehand. So that's exactly what this decorator does. This memoized decorator says, you give me a function, and I'm going to spin up a cache. And what I'm going to do is just decorate around your function to have it read into the cache before trying to compute. So all you need to do in order to make this fast is to do this. Right, there is a decorator for taking a recursive function and making it a dynamic program, right? By automating this fact that there's cache over it. Like one of the topics for this lecture that I was actually thinking about doing was just giving a whole hour about Python decorators. They're like so cool, but you should know that this decorator exists. So at my interview, they said, make your recursive function fast, and all I did was write @memoize over it. And I said, there you go. It gets a cache, okay? So that's what I wanted to leave you with today. I think we actually did get through everything. Everything I said is in the slides. I also gave the UQ Society my code. If you want to get the full version of this, if you want to learn about recursion for 13 weeks with me, we're in week 12. We finally print Hello World because it does take 12 weeks for me to develop the theory to print Hello World in the functional paradigm. I welcome you to come take Comp 3400. It's a very neat course where we're obligated to program everything recursively. By the end of it, recursion will feel like a friend that you have with you like that. But I hope today that I've made you at least think about reaching for the recursive tool instead of being scared of it. Because you don't have to be scared of it, because you don't really have to understand it. Right? All I want you to do to leave today is to think, when I'm designing a recursive function, I'm going to just assume that the function works already when programming it. And if I think, how does it work? You just think by magic, right? It just works. And if you program with that philosophy, you're going to be able to program recursively. So thank you. That's my time today. Thanks for showing up. All right. Can I click out of this? Look, recursion.
Does anyone have any questions? Okay, well, good.
Good.
Thank you, Paul. We have a
Recursive wave. All right. Should I
Just click stop streaming.
stop?
Bottom right. Stop streaming over here.